Morning, everyone. So yesterday we introduced our redox chapter. Essentially, it's a reaction that involves electrons being transferred. We saw some definitions. The oxidation is a thing that lost electrons. It passed the electrons over to the thing that gets reduced. I'm just going to give you a quick practice question, just seeing if you're okay with the terminology. I would actually, when you read questions like this, I would just translate it for myself. We'll see in a second here. All I want you to do for this one, I want you to identify which species. Identify the species oxidized. Identify the species reduced. And we talked about something called the oxidizing agent and the reducing agent. Just a hint here, these are always referring to the reactants. Okay, so I'm going to give you an easier formula first. So let's go from ClO2 minus. Let's say it becomes ClO3 minus and Cl minus. The other one here we'll do is Mn plus 2 and BiO3 minus becomes MnO4 and Bi plus 3. Okay, I'd encourage you just to pause the video, try it out for yourself. Okay, assuming you've done that here, you can check your work with me. If the question, like I've worded it here, if the question is just identify which is which, I would just do oxidation number, right? We're going to see in this lesson here, balancing works, sort of 3/4 of the way through your balancing, you'll find out which is oxidation and reduction, but you're going to see it's a lot of work. If the question is just identifying, it's easy enough just to do it with oxidation number, okay? So I'll show you how that works here. We'll start off with the first one. This is a very special type of reaction. It's called a disproportionation reaction. Remember, this is one chemical that's doing both the oxidation and reduction. Let's find the oxidation numbers of absolutely everything. So pretending everything is ionic here, oxygen here is usually a -2. There's 2 of them that gives -4. Chlorine minus these 4 have to give you a -1. This chlorine here is like being oxidized plus 3. That is not a real charge, but if I see this number go up, I know it's oxidation. If I see it go down, I know it's reduction. In a similar fashion here, the O, oxygen is -2. There's 3 of them this time, -6. The chlorine here is kind of like a +5. Well, chlorine going from 3 to a 5 state actually helps identify my oxidation number has increased, so therefore it's an oxidation. Then you say, well, the alliance is GER. Well, the oxidation is actually a loss of electrons. So I would have to have lost electrons to become ClO3 minus. That would imply to me that the other change here should be reduction. I need to have one guy willing to lose electrons, one guy willing to pick it up. In this case here, Cl is just a simple ion, so that actually just has a charge of -1. What's the change there? If I go from kind of like a 3 to a -1, that's going to be a drop by 4. My oxidation number has gone down. That automatically means reduction. Again, it's a little bit weird to think of why is the reduction a gain? It's just the things that I'm gaining are actually negative, so it's bringing my charge down. So in this case here, kind of boring because, well, it's just ClO2 minus, okay? So in the one case here, if I just list it that way here, this one here is currently being oxidized. This other one here is being reduced, let's say, in becoming the chloride here, okay? So that's how you identify here. Again, just a hint for yourself. Yes, it just happens to end up forming this ClO3 minus and the Cl minus, but whenever they're asking us just to identify these, they're just asking for the reactants. Okay, so it's going to be a little bit more clear in the second one here, which is oxidizing agent. It's a little bit hard to do. I just want to remind you of that term here. This is called the disproportionation reaction. Disproportionation. Let's do the second one here. We can even balance this one later on, but it's going to be quite a pain. You're going to see in this lesson. But let's just go through. We're just asked to identify. So we're asked between the permanganate and the BiO3 minus, I want to know which one here is oxidized, reduced, who are the agents. So manganese is going from a charge of +2. Later on, oxygen here is -2. There's 4 of them, -8. Manganese is +7. Going from 2 to 7 means my oxidation number has gained by 5. So therefore, the chemical that was involved, the reactant that was involved here, has been oxidized. Therefore, I would expect the BiO3 minus to have been reduced. Let's check the charges. Oxygen is usually -2. There's 3 of them, -6. So this bismuth here is like going from a +5 going to a +3. Good. That one there is a -2 oxidation number, and therefore that means a reduction. So therefore, the reactant that was involved in doing that, it was the BiO3 minus that gained electrons. It just happens to become Bi plus 3 later on. Who are your agents then? Who actually allowed the BiO3 minus to actually reduce? If manganese plus 2 were not here, it wouldn't the BiO3 wouldn't be able to gain electrons. So manganese is also the reducing agent. Typically, in doing so, it gets oxidized, and therefore BiO3 minus is also the oxidizing agent. Again, if it weren't confusing enough here just with terminology, an agent is just present to help something else oxidize or reduce. Okay. In today's lesson, we're going to flesh it out a little bit here. We're going to learn two different methods to actually do balancing. In the IB exam, they're just going to ask you balance. It doesn't matter which way you do it. This first way here is sort of a brute force method. It always works, although it can be fairly tedious. And I'm going to show you a shortcut way. If it's a fairly simple looking formula, I try to balance it the easier way, but let's just go through both anyways. So in terms of balancing here, this first method, just in general, is referred to as the half reaction method. Just let me give you an overview idea here. Half reaction method, I know I have an entire equation. This one here should be a whole oxidation reduction reaction here. It's too hard to balance all at once. You're going to break up the two half reactions. You're going to balance off the bits. Balance off, here's what the oxidation looks like, here's what the reduction looks like, and then put it back up together. So this first right here is just practice here. We actually just have a half equation. I want to see how I'm going to balance just part of it. And then on the next page over, you're going to see us do this twice and then put it back together. Okay. So all redox reactions here involve one guy oxidized, one guy reduced. We can split them into two half equations here. Each half equation, as well as the full equation, has to be balanced for mass. So that's sort of balanced for number of atoms. That's how we've been balancing conservation of mass. The number of atoms has to be the same on both sides, but we also need a balance for charge. No, there's balance for a charge here. The total charge doesn't have to be 0, but the total charge has to be the same on both sides. This guarantees that I have the same number of electrons on left side and right side. So just for practice here, this is sort of partway already through a half reaction method. They already have one half reaction. How do I know this is not a full redox reaction? I just have one chemical becoming one chemical. Here's a nice hint for yourself. I have a ruthenium chemical becoming ruthenium. Probably something has happened to ruthenium. If I were just asking you where was it oxidized or reduced, you can just check charges again. This is ruthenium elemento, so 0. This is it as a compound, so probably something has changed. Oxygen is -2, so ruthenium here is +4. Oh, look, 4 actually became 0, so I know the forward reaction is actually being reduced. This time, not just telling me, yeah, it gained electrons, I actually want to know how many electrons it gained. For balancing these half equations here, there's a nice little mnemonic. You can say to yourself here, we're going to balance off our major atoms first. Then, just as a shorthand here, major hydroxide. Our major atoms are everything except for O and H. Those are going to balance later on. You balance that by inspection. So anything that's not oxygen or hydrogen, like ruthenium, I have one ruthenium, albeit in compound. I have one ruthenium. Perfect. Done. So I've done the first step here. My major atoms are balanced. I have one ruthenium on both sides. Next step, we're going to balance our oxygens. Right? Oxygen comes in a lot of redox reactions here. And usually a lot of these redox reactions, because they involve charges, water is a very common appearance. So we're actually going to balance oxygens by adding waters. So on the left side, I have 2 oxygens. On the right side, I have no oxygens. So what I'm going to do is I'm actually going to add 2 waters to the right-hand side. So RuO2. Balancing in redox is really, really systematic. It would be really hard to do this by inspection. How would I know there would actually be 2 waters come out? And again, I knew I needed 2 waters. Every water only has 1 oxygen, but I had 2 oxygens, so I needed to make sure that at least the number of oxygens is balanced. Okay. Next step here is you're going to balance the H's. In IB, the balancing that we're going to do is always in acidic solution, so we're going to balance H's with H+. So at first, I had no H's, but now that I've actually added waters, I actually have 4 equivalent H's. I have no H's on the left side. I'm going to add 4 H pluses to the left-hand side. So again, just following through this really systematic procedure here. Balance the majors first, balance the oxygens with water, balance the hydrogens with H+. And then at long last, if you check, we're actually good for number. 1 ruthenium, 2 oxygens, 4 hydrogens. We're actually good for the number part. Balancing charge is going to be the last part. Because this one here is a half equation, this one here does allow for free electrons. And what we want to do is we want to make sure the total charge on both sides is the same. The total charge on the right side, elemento, so it's 0. Over on this side, the RuO2 is 0. Every H is a +1, but I have 4 of them. In total, I have like a +4 on this side, like a 0 on this side. You're always going to add electrons to the side that has a higher charge to bring that charge so that they equal. So what I'm going to do is I'm going to add 4 electrons to the left side. 4 electrons plus 4H plus, and RuO2 becomes Ru, and 2H2O. And if you check that, we just checked in terms of number already, but now checking in terms of charges, I had 4 net positive charges with the 4 free electrons. It also cancels out the charge. I have 0 overcharge on both sides. Okay, this is completely balanced. We saw briefly last day, if electrons are on the left-hand side, we know this is a reduction reaction. Who is the chemical that gained these chemicals? It's the reactant that actually gained the electrons. So the ruthenium in RuO2 has been reduced. It just happens to become Ru later on. That's actually what we're going to do just to a half equation. Because the redox equation contains 2 half reactions, we're going to need to do this twice. Okay. So just for practice here, we have an unbalanced full equation. How do I know it's a full equation? I have 2 things becoming 2 things. First thing you're going to do is you're going to say, this thing here is too hard to balance altogether. What we're going to do is we're going to try to balance off, break them up into 2 half equations first. How to identify the half equations? Look for chemicals that look the same. Right? So for example, the Mn2 plus probably becomes the other compound that has Mn inside. So one half equation will involve Mn plus 2. Make sure you carry down all the charges, everything as is. MnO4, permanganate with a -1 charge. That's probably one half equation. The BiO3 minus. Earlier in the warm-up question, we had already identified who was oxidized, who was reduced. But this time, they actually want you to figure out how many electrons are being transferred. What does your full equation look like when the number of atoms are matched for and the charges are matched for? Okay, so using the method that we used up above here, you saw this method here. It can be many, many lines, right? So take up a lot of space on your page. Usually what I do is I write it sort of in the middle of the page, and I start adding things left side to right side, so at least I can do everything along just one line. So case in point here. Let's balance each half cell using that major hydroxide strategy. So taking this first equation, I'm going to write it sort of in the middle of my page here. I'm going to say to myself, I need to balance major atoms first. Major atoms here are the manganese. So one manganese, sure, one's charged, that's fine, doesn't matter. One manganese. Balance the oxygens with water. I had no oxygens here, I have 4 oxygens there. I'm going to balance it with 4 waters on the left-hand side. That screws up the H's, but that's fine. H's come afterwards. I'm going to balance H's with a plus. In total, I have 8 H's. No H's there, no H's there. So I'm going to add 8 H plus to the right side. So you see me just going left side and right side. I still, at this point here, have no clue who's oxidized or reduced. It's at this last step of balancing for charge. When you add those free electrons, if you added them to the left side, like we just did, it's a reduction. In this case here, the total charge on the left side is plus 2. The total charge on the right side, each permanganate is -1. Every H is +1, but there's 8 of them. The total charge is +7. I'm going to add electrons to the side that has a higher charge, and I'm going to add it until they're equal. They don't have to be 0. In this case here, I'm going to add 5 electrons, and therefore +7 minus these 5 gives you +2 on both sides. At least the total charge is the same. And now, because the electrons, oh look, they're on the right-hand side, I at this point know it's oxidation. I know it's the Mn plus 2 that was oxidized. I just need this water and the H plus to help me with the balancing. Second step here, we're going to do as a reduction. I have to have 1 of each. So the bismuth-looking compound here, BiO3 minus, becoming Bi plus 3. Balance for major atoms. I have 1 bismuth, fine, no problem. I'm going to balance the oxygens. I had 3 oxygens, no oxygens yet. So this time I'm going to add 3 waters to the right-hand side. Balance for H's with the H plus, so I have 3 times 2, so 6 H's on the right, so I need 6 H pluses on the left side. Now the number of atoms are accounted for. Let's balance for total charge. The total charge on the right side, because of the bismuth, is +3. The total charge on the left side, the BiO3 had 1 minus. Every hydrogen has +1, but I have 6 of them. 6 minus 1 is +5 currently. So which side and how many electrons should I add to make sure it's balanced? For the half equation, we can have free electrons. You should be able to tell me I'm going to gain 2 electrons on this side here. This one here, electrons on the left side. So again, it's the reactant. It was the bismuth and this BiO3 minus that actually got reduced. So you see, it's quite a lot of work, right? I had to break up the half equations, follow the major hydroxide acronym here, balance both parts. I'm not quite done yet because I've artificially broken these compounds up. Now what I want to do is I want to actually put them back together into one big equation. And the key here is your big equation cannot contain free electrons. We're going to make it in such a way that the electrons end up canceling out. Every time you run the first reaction, the manganese plus 2 loses 5. If I just run this BiO3 reaction just once, it only gains 2. Then I would have 3 free electrons. That's unstable. Well, just because each of these half equations themselves are balanced doesn't mean I need to run them in the same ratio. What I can do here is actually find the lowest common multiple between 2 and 5. Well, both 2 and 5 actually go into 10. Every time let's run this first reaction twice, let's run the second reaction 5 times. And in that case there, the 2 is going to lose 10 electrons total. I run this second reaction 5 times, I'm going to pick up all 10 reactions. That 2 basically needs to be scaled in for everything. So I'm going to show you this sort of middle step here. Everything gets multiplied by 2. So I'm going to have 8 waters and 2 manganese. I already made sure that my half equation was balanced. So as long as I scale this 2 here properly in, everything's going to still be balanced. Run the second reaction 5 times. So again, I set it up so that I had 10 electrons. 5 times 6 is 30. I have 5 BiO3. This becomes 5 Bi plus 3 and 15 waters. We had set it up in such a way that my overall equation, the 10 that was lost from the Mn plus 2, all gets picked up, and now we have the overall. Pretty much everything here on the left side should be on the reactant side. Everything here should be on the right-hand side. There are chemicals that are going to cancel out, so let's try it here. So I have 8 waters and 2 manganeses. I have 30 H plus and 5 BiO3 minus. This becomes 2 permanganate, 16 H plus, and 5 Bi plus 3 and 15 waters. Okay. So if I copied everything correctly here, this one here should still be balanced here. Because when we were balancing the half equations, we were adding water, we were adding H pluses. There was no guarantee they were added to the same side. Very often at this point, you're going to have different numbers of H plus. So I have 16 on this side, I have 30 on this side. Even though they're not going to completely cancel, let's get rid of those 16. Let's minus this by 16, so that leaves me with 14. I also have 8 waters, and I have 15 waters over here. Let's get rid of the 8 on this side, and let's make that 7. We want to make it as simple as we can. And there we're done. So we have 2 manganese plus 2 and 14 H plus, and 5 BiO3 minus is now becoming 2 MnO4 minus, 5 Bi plus 3, and we had 7 waters. Okay. This was now a fully balanced redox equation. You can check that it's balanced in terms of number. Make sure all the atoms are accounted for. 2 manganese, 14 H's, 7 times 2 is 14. 5 bismuth, 5 bismuth, 5 times 3 is 15 oxygens, 2 times 4 is 8, plus these 7 over here is 15. Number is good. You want to check for total charge. Usually I don't have time to check for number of atoms. I'm going to assume that's right. If your total charge matches up, you're probably okay. So what's the total charge? I have 2 times 2, so it's plus 4, plus the 14 here, so that's going to be plus 18, minus the 5 from here, so plus 13 is my total charge on the left side. On the right side, I have minus 2. 5 times 3 is plus 15. 15 minus 2 is plus 13. Water is neutral. Again, the charges don't have to be 0, but they have to be the same on both sides. The charges are equal. That means there's no free electrons in my balanced redox equation. Usually, I would actually say this is actually balanced in terms of acidic solutions because, I actually have a net lot of H+. We're going to find there are these balanced half equations actually in the data booklet. They're already all balanced for you. So all you're going to do is just the lowest common multiple step later on. But at least I want you to know how to balance it because they're definitely going to ask you. Separate the half reactions and then just balance it all at once. Just as a nice little practice and spin off here, there is one more practice for you on the back side. What I'm going to do is I'm going to balance this first one just for argument's sake here. I'm going to balance it in what's referred to as basic solution. In IB, technically, we don't actually need to do basic, but all that basic entails is we don't have no excess H+. We actually don't have a lot of H pluses around. Okay, so I'm just going to demonstrate this procedure for you. Turns out, even though in IB they're only going to ask you acidic, even if they just say blank here, you can assume it's acidic. You just balance everything in acidic. For basic, you just add one last step out towards the really, really end. And I'm just going to show you what that last step is going to be. Okay, so example number 1. How do I know this is a full redox equation? I have 2 things becoming 2 things. First thing you're going to do, it's too hard to balance sort of all in one step. So what we're going to do is we're going to break up the 2 half reactions. Probably the Fe plus 2 becomes the Fe plus 3. Probably the chromium compound, the chromium becomes the other chromium compound. Right? That's breaking up the 2 half reactions. What we're going to do afterwards is we're going to follow our major hydroxide, that was our mnemonic. Don't forget to do this major step. Because if you, oh yeah, let's just add water, let's just add H pluses, and you realize, hey, the major atoms don't balance, then you need to do it all over again. So check the major atoms is always a step that people forget. In this case here, we have one iron, perfect. 2 chromiums, oh, and then 1 chromium. I'm just going to do that by inspection. I'm just going to randomly add a 2 there. Yes, that screws with the charges, but remember, we're going to balance the charge at the really, really end anyways. Okay, so we have that situation here. I'm going to balance for oxygens. Well, there's no oxygens in the iron equation. I have 7 oxygens on the left, no oxygens on the right, so I'm going to add 7 waters. We're going to add water. Most of these reactions take place in aqueous. We're going to add H+. Even though I'm going to show you how to do it in basic, you're going to balance it as if it were acidic. So I'm going to add H pluses here. Again, no H's in the first equation. That's already balanced. No H's. In this case here is because of the waters. There's H's. 7 times 2 is 14. I'm actually going to add 14 H pluses to the left-hand side. Again, just get some practice adding left, adding right, just make sure things are balanced. And then finally for the iron equation, well, the only thing that wasn't balanced, the numbers matched up, no O's, no H's, it's just the charge. So what we're going to have is we're going to have +2 as the total charge, +3 on this side. I want to add 1 free electron. It's at that electron step that we actually identify. This first equation is actually the oxidation reaction. It's the Fe+2, the reactant involved that was oxidized. How about for the second equation? What's the total charge? The total charge is a -2 plus the 14 there. I have a total of +12. On the right-hand side, here's where the major atom matters. 2 times 3 actually is already a +6. I need to add 6 electrons to the left-hand side to make sure that each half equation is internally balanced. Okay, this is referred to as a reduction reaction because the electrons on the left-hand side, it's the chromium in the dichromate compound that actually gets reduced. It's the reactant that actually has gained electrons. It's just we needed these H+ just to do the balancing. So last step here, we're going to just do lowest common multiple. I want to make sure that in my full equation that there's no free electrons. So what we're going to do is we're going to, both of these numbers go into 6. So I'm going to take the oxidation reaction and I'm going to scale this up by 6. And that's basically going to set it up so the electrons cancel out. So all these on the left side should stay on the left. So we're going to have 6 Fe+2. I didn't need to do anything to the reduction reaction here. I'm just going to run that once. I had already set up so the electrons cancel out. I'm not going to bother writing that. So Cr2O7 minus 2. I need to scale up the iron +3, so 6 Fe+3. Again, the electrons were set up to cancel out with lowest common multiple. I'm just going to copy down the rest here, 2 Cr+3 and 7 waters. Okay. Again, in IB, they would usually just say balance this. Even if they didn't say acidic or they mentioned bracket acidic, that would be your answer is acidic. Fine. I just gave you this added little extension. This is actually something they do in regular Chem 12. If it is basic, what they're implying is, wait a second, there shouldn't be excess acid around. And in fact, we're going to see later on, these H+ are actually important. If H+ weren't present, this reaction wouldn't actually be able to transfer electrons. H+ is actually needed, not just for the balancing, not just to make it look good and match up. H+ is actually needs to be in the reaction for this to happen. No acidic conditions can happen. So what we're going to do here, I did ask you just for practice sake here, do this in basic. Pretty much we've done everything as you would in acidic. Balance it as if it was acidic. And what you're going to do as a very, very last step is you're going to say, well, wait a second. In basic solution, we don't have a lot of H+. This last part here is going to be for the basic. If they ask you for basic, what I want you to do is I want you to get rid of the H+. How do we neutralize H+? What we're going to need to do is we're going to need to add hydroxide. So you're going to add hydroxide. This is one way of doing it. Since H+ reacts in OH- in a 1-to-1 ratio, I need to add 14 OH-. Well, this one here, we're actually balanced to begin with. If I added 14 on this side, I better add 14 on this side here. And therefore, yes, in some sense, the H+ and the hydroxide, they kill each other off. They don't just vanish, though. This ends up becoming 14 waters. And oh, look, now I have waters again. So therefore, I can cancel. Well, let's get rid of these 7 waters, and let's make this a 7. And therefore, in basic, if I don't have an excess of H+, if I still wanted this reaction to occur, probably it's not going to be as efficient. 7 waters reacts with the dichromate. This right here, from a balancing standpoint, should still be balanced, right? Because algebraically, I did the same thing to the left side, the same thing to the right side. Don't forget to add the 14 OH minuses, okay? Again, normally if I'm just checking my work, always good to do that. Usually I don't have time to check for the number of atoms. If by this time the total charge is actually the same on both sides, probably we're good. So what's the total charge on the left? 6 times 2 is plus 12, minus these two here, the total charge is plus 10. On this side here, we have 6 times 3 is 18, plus these 6 here, so we have 24, minus these 14, plus 10, plus 10, plus 10, we should be good. Okay. So again, in IB, they typically won't ask you to balance in basic, but you see that it's not that much harder. It's just that one last step towards the end. I'm going to show you one other way that they convert to basic, just for completeness sake here. Let's say we were at this part. I have everything balanced in acidic. Everything is good. 6Fe plus 2 and 14H pluses. Again, very tedious to do balancing, but very systematic. 6Fe plus 3 and 2Cr plus 3. Earlier I had 7 waters. What I did was perfectly fine, just adding 14 OH minuses. What you can add is you can actually add it in such a way. I know the H plus is on the left side. Another way of doing this very last step, only for basic, let me make this note, only if they ask you for balancing in basic, what I want you to add is that self-ionization of water. So if I have H plus on the left side, I want to add H plus on the right side. I have 14 of them. What if I had 14 waters? The self-ionization here is water has a slight capacity to break up into 14H plus, 14OH minus. I know the KW is very tiny, it doesn't do that very well, but at least from a balancing standpoint here, this would end up canceling the 14H pluses. We would have the 14OH minuses as we had earlier. It would still give us 14 waters. I can cancel those 7 there, 7, and that cancels out, and that leaves you with the same expression. Okay, so whichever way you like doing for balancing, you can do it that way. So lastly, just for completeness sake here, I just want to practice. Again, in IB, pretty much all they're going to say is just balance. They're not going to force you to do this method. We've been practicing half reaction method. Separate the two half reactions, balance the two parts, lowest common multiple, and put them back together. If it's basic, you add this one last step. I'm going to give you the second method. They're not going to force you to balance it using half reaction, or the second method here called balance using oxidation number method. Okay, so just balance. Usually I find this oxidation number method, it's a little bit simpler because we're actually not having to break up the two parts. Their end goal is just making sure that it's balanced. It's totally up to you which method you use. So I just want to give you more ways of doing it so that in case you get stuck going one way, you can try it the other way. What was the name for this reaction here where you have one chemical actually undergoing both? Hopefully you can say to me disproportionation reaction. Again, just for simplicity, even if this were half reaction method, I would be saying, well, the chlorine probably becomes a ClO3 minus. In the other reaction, the chlorine becomes Cl minus. Just to make that easier to look at, I'm just going to repeat this chlorate ion here. Okay, so I have that there. This time what I'm going to do, totally different method of balancing. I'm going to give you the steps here. I want you to find the oxidation numbers of everything. Right, that's something we didn't have to do in the half reaction method. Okay, I want you to balance the change in oxidation number. Okay, we'll see that with just looking at the oxidation, who's gaining and who's lost. And then as a last step, you're going to add water for the O's and add H pluses for the hydrogens. So if you're thinking about our acronym from before, it used to be major hydroxide. It used to be, let's balance the major atoms first, and then oxygen, hydrogen, charge. We're going to still make sure the major atoms are balanced. That is still an important step. But what I'm going to do is I'm actually going to balance the charge before balancing the oxygens and the hydrogens. Okay, so let's find the oxidation numbers for absolutely everything. This is a good way of actually identifying who's oxidized and who's reduced. So let's go through here. Hopefully you got a lot of practice by now. Oxygen is -2. There's 2 of them, -4. This chlorine is +3. So that's +3 as well. Oxygen is -2, -6. So this chlorine is +5. This chlorine here is -1. We're going to track the changes. Whenever your oxidation number, whenever this fake charge goes up, it's like having lost electrons. Oxidation number increase means I've been oxidized. I had to lose electrons. I had to lose 2 electrons, in fact. On the other case here, I'm going from +3 down to -1. First thing, it's a drop. Oxidation number has gone down. So far, we've just been saying reduced. For this oxidation number method, I actually want to know how much. So the 3 going to 5, I've actually gained by 2. The plus 3 going down to -1, I'm actually going down by -4. Okay? So we have this situation here. Notice in this step here, I'm not actually going to break up half reactions. So what I'm going to do is I'm going to try to balance the charges at this point. Every time the ClO2 minus becomes ClO3 minus, it's going to gain 2. The other one loses 4. What's the lowest common multiple between +2 and -4? Well, if I run this first reaction, everything involved in this +2 change, if I run this reaction twice, that's going to end up net +4, and that's going to counteract this -4. So everything that's involved in this, which is this middle equation here, I just need to put a 2 and a 2 there, right? I'm not breaking out half reactions. I just did that, and somewhere behind the scenes, it would have balanced for charges. It may or may not be balanced in terms of oxygens. Let's just check it now. We have 2 oxygens plus the 2 times 2, so 6 oxygens. 2 times 3 actually works out good. 6 oxygens. How many hydrogens? Well, no hydrogens on either side, so we're perfectly balanced. And on this disproportionation reaction, because we just had one reactant doing both parts, we're going to say this is 3 ClO2 minus becomes 2 ClO3 minus and Cl minus. In fact, even though I was ready to add waters and add hydrogens or whatever, the oxygens already matched up. In fact, you could have just done this by inspection. If you were to guess, well, the oxygen was 3 and the oxygen was 2, let's 3 times 2 make that a 6, and this 2 times 3 turns out just coincidentally, pure chance, that actually is the balance equation. That actually is already balanced in terms of number and actually balanced in terms of charge already. Okay. More often than not, it isn't like that. Okay. If it were basic at that point here, because there actually are no H pluses on left side or right side, there's nothing to get rid of, this would work in basic as well. Okay. So what I want you to do here, again, this is a standard problem here. They're just going to ask you to balance, totally up to you. You can do half reaction method. You can separate the two halves, balance the bits, and then put them back together. Or you can try this new oxidation number method. Be really careful. I'm going to show you this on the next lesson here, but be really careful that oxidation numbers are quoted per atom. So if I actually had 2 chlorines undergoing this change here, that change would actually be doubled. We'll see that actually in tomorrow's lesson. They're just going to say balance. You can assume that these are all in acidic conditions and just see how you do. They've already given you all the answers here. The relative order doesn't matter. You can put the uranium first, permanganate first, but it just needs to make sure all the chemicals on the left should be on the left, all the ones on the right should be on the right. Okay, so just do a lot of practice with that. We'll pick it up from there tomorrow. Thanks, guys.